Hello everyone. Today we will be looking at a 2D graph, as for example like this, and we will be analyzing how the unit tangent vector, what the unit tangent vector is, and also we will be analyzing what the principal normal is, as well as the curvature and the radius of curvature. Okay, so let's start. So first of all, let us see what tangent vectors really are. So let's see at this point, the tangent is in this direction, the tangent unit vector. You can do the opposite as well, like in this direction, but I'm going to use a convention like we will start from here to and here. So we will follow the same convention, okay? And then the next tangent vector will be here. Then the next one here. Then the next one here. Okay. So all of these are tangent vectors, but there is a point here. Okay, there is a point here. Let's say these tangent vectors are specified as t cap, t cap, t cap, and t cap. Okay, so there is one information that we know, that tangent unit vectors have the magnitude of 1. Okay, so if we are to say like this, t dot t, what does it mean? T squared, right? Which will be equal to, of course, 1. So t squared or t dot t is equal 1. So t dot t is equal 1. If we differentiate both sides, or I think we can take the differential, then d of t dot t will be equal to 0, because the differential of constant is 0. And using the rule of differentiation, you will find that it will be t dot dt plus dt dot t, which will be equal to 0, of course. And you will get here that 2t dot dt is equal to 0. And you can just divide both sides by 2 and get something like this, that looks like this. Okay, so what are we really seeing here? We have imposed the condition that the magnitude of t will be 1 and the direction will change. So if the direction can change, t is a vector of a fixed magnitude 1, and only its direction can change, its magnitude can. So this means that t and dt, these both are perpendicular. So as for instance, um the the tangent unit vector is this. Okay, and then there are two ways in two dimensions. Of course, in two dimensions there are two ways that it can produce a perpendicular vector, this and this. So which one? That's a question, and that needs to be answered. Okay, but there is one thing for certain, that if t is to change, then it has to be through one of these vectors, either the upward direction or the downward direction. You can say anything you want, like let's say this is the positive direction, negative direction, whatever you say. Okay, it doesn't really matter actually, but if t changes, or the tangent unit vector changes in one of these two directions, only then it can retain its magnitude. Okay, and if it doesn't do that, then the magnitude of it will change. Okay, because we have come from the condition of it having the fixed magnitude, unit vector, so of course the magnitude is 1. Now what we will do is follow it from here, and we will differentiate it with respect to a parameter else. I will show you in a minute what actually is, what is s actually. Okay, so d ds of t dot t is equal to d ds of 1. Of course, the right side is 0, and the left side will give us, in the same manner, 2 t dot dt ds. Okay, so you will find that t dot dt ds is equal to 0. So this time the vector t and dt ds, they are perpendicular to each other, and we will define this one, like we will define this one to be, like let me show you, dt ds, we will define this to be kappa n, and this will be the normal vector, principal normal vector, I mean, principal normal vector. There is another definition that we can use, which is gt gs is equal to normal vector divided by rho, and we will call this the radius of curvature. We'll see later why we are calling this the radius of curvature. And okay, this is the principal normal vector, and this thing is called curvature. We'll not get into too details of this, but we'll continue like this. I will show you the analogy, that why this is considered to be the radius of curvature, and why is this the curvature, what does it really mean. And of course I haven't even shown you the parameter yet. What does this parameter mean? actually ds corresponds to the arc length, where, let me show you. Let's say uh, at some instance, I think you can say from here to here, let's say this will be considered ds, and from here to here you will consider another ds, and of course when you step from here to here, then the t unit vector or the tangent unit vector changes its direction, right? And how does it changes? How does it change its direction? The initial t was here, the final t was here. As both of these have unit magnitude, then it falls within a unit circle, right? So what we can really see here is this is the initial one, and this is the final one. And within ds, like let's say they are like when you go around ds in that direction, in the right direction, here we are using a fixed rule, like from left to right, ds is positive. Okay, so from initial to final, like you can see, like this is going anti-clockwise. I mean, sorry, my bad. It's going clockwise, right? Clockwise, and the change dt is downward, right? Downward. And if we incorporate this, then what will we really see is, if you try to make it small, like because dt must be really small, and the ds must also be really small, so the tangent vector, the direction will not really change so much, so the angle will be really small, and like this. Okay, so it is almost perpendicular, right? So for every point, dt must be perpendicular. We have already seen that in in mathematical, right? Like this, right? So this dt is perpendicular, and perpendicular to what? Perpendicular to the tangent unit vector. And as you can already see here, for this vector, the normal vector must be in this direction. Like normal unit vector, it must also have the same magnitude. So I'll do this straight up. And for this, it will be in this direction. And for these two, there is a difference. Just take a quick look. Here, y, the second differentiation of y with respect to x, and we're considering this as y and this is x. Okay, so this is less than 0, and here the second derivative is greater than 0. Okay, so for both of which we will consider this is the initial, this is to be the final. Okay, so this is the initial one, this is the final one. Okay, and change direction this direction, and if we consider ds to be really small, then the direction must be in this direction. Okay, the direction must be this. And also for, oh my god, for this the direction must be something like this. Okay, so for concave down we will get something like this, and for concave up we will get something like this. And it does really make sense. We're going to uh, show you what it actually means. And as you already know, the velocity is always in the tangential direction, right? So velocity here, velocity here. The change in velocity must also correspond to the change in tangent vector. What we really mean? Like here, let's see. Okay, we're trying to see what this really means. So initially, let's say that unit tangent vector is here, and then at some later point, at some later moment, the unit tangent vector is this, and we will see. So we will denote it as t prime. Okay, so t and t prime. The initial velocity vector will be this p, and the final velocity vector, like after some time, must be here p prime. What is the change in velocity vector? This will be corresponding like this. Okay, must be. Okay, it must be. This here doesn't give you a clear message. Okay, so if we try to look at it in a way where the angle is very small, infinitesimally small in fact, then it will be something like this. I think I should make it much smaller. Okay, like this. I think this should be enough. So this is dt. This is change in unit tangent vector, and I think I will put it at the left section. Okay, so let's say some initial velocity was v, and some final velocity was v prime. Okay, so one thing to note, the change in velocity will be this. The change in velocity will be this. Okay, I don't need to change anything. The change in velocity will be this. But one thing, this is the t initial and this is the t final. So there is a component parallel to dt. Okay, a component parallel to dt, and there is another component which is parallel to t. And as we've already told you, this is the t vector, this is the direction of the t vector, and this is the direction of dt vector scaled by something, so I don't really need that, but it is still perpendicular. Okay, so we are dissolving this vector into two components, two perpendicular components, one of which goes to dt, and another part of the change in velocity vector goes to the tangent unit direction, unit tangent vector direction. Okay, so there are two components. Okay, recall that the perpendicular portion, just how dt changes if as the magnitude of t is not changing, just how it dt is perpendicular to t, this perpendicular portion of del v, or the change in velocity, must correspond to the change in direction, and this one must correspond to the change in speed. So now we are okay to do some stuff. Okay, as you can already see, if del v is here, then acceleration is also here, and this is one component of acceleration, this is another component of acceleration. Not really component, we have to divide it by del t, but we are setting it aside now because we are only dealing with directions. Okay, so if we are only dealing with directions, then you can see that there is a component of acceleration which is, by the way, in the same direction as dt. So component. Okay, so let's go to another section. Now, as we define and as we know, okay, the curve is this, and as we know that t vector is here and the change in t vector must be in this direction, and so if we parameterize the curve from here to here, like from this point to this point, and let's say at t is equal to 0, this is the parameter here is t, and the s really represents the distance from this position, distance from a, let's say a to b, distance from a is characterized by s, and whose parameter is t. S itself is a parameter which is the distance parameter for now. So for the change in s, like for the change in s, which we will call ds, for a change in ds, there is corresponding change in the tangent unit vector. So of course there will be some change. Okay, and we define dt ds as n normal vector, and of course we have already found normal vector here. These are normal vectors, n divided by rho, where rho is radius of curvature. Okay, so now we are going to set something up. As s corresponds to distance from a, thus ds dt means the speed. This is the speed the particle is going. Okay, and t is the parameter, time parameter. Okay, so what we can really do now is characterize the velocity vector v, which is magnitude, and the direction. The direction is always tangential, so we can use the tangent direction. I mean the tangent unit vector. And the acceleration will be the change of velocity vector with respect to time, right? So we can now do change it. So v vector dv dt plus v dt dt. Okay. So we can do simple stuff here, which is we can show that we can use we can do something like this: dt divided by ds, dt divided by ds, and then we will get what we'll get is plus v ds dt dt ds, and we have already defined it to be normal divided by rho, radius of curvature. So this is v squared, this is also v, so dv dt d vector unit vector plus v squared, and this will come out, this rho will come out, right? So divided by rho normal vector. So what is this actually? This is the acceleration vector, right? Acceleration vector has two components: dv dt t, and v squared divided by rho n. Okay, so this is the rate of change of speed. Rate of change of speed. Okay, fine. So this is the acceleration vector, general acceleration vector in two dimension, of course, 2D. Okay, so what can we really do now? What can we really do now? We already know that the acceleration must be equal to negative v squared divided by r when and the direction must be negative r. Okay, so the direction, I think the direction I should show you like this. Is it the r unit vector? Yeah, r unit vector. Okay, fine. What can we really do now? So we can apply this formula for our circle. The circle we have shown already in another video. I think this should be enough. Okay, so for every point here on circle, the acceleration is towards the center, and this is the radius vector. Let's say this is the unit radius vector, and this is the negative unit radius vector. Okay, for this point, of course, for this point, for every point there is different radius unit vectors or unit radius vectors, whatever you say. So this is our vector, whatever it changes, right? So for this point, just how normal normal vector changes, right? Okay, so this thing, if we try to apply this one, if it is uniform circular motion, then dv dt will be equal to 0 because there is no change in speed, right? So the rate of change of speed is of course 0. So from here we will find it to be a is equal to v squared divided by rho n. Okay, and from here we already know that a must be equal to v squared divided by, I think I will use the big R, the capital R, then the negative R immediately. So what's the difference? Let's say at some really arbitrary point. Let's say this is the arbitrary point, and in the next moment the t changes from there to here. So of course the normal vector, which is perpendicular to t, must be in this direction. And there is a simple thing to notice here. The normal vector has unit magnitude, and the negative sign here only means the direction, right? Like the positive here means the outward direction, and negative here means the inward direction. So actually this and these both are similar, and of course if they both are the same vector, then their magnitude must be the same, v squared divided by rho, and from here you get v squared divided by r, and you see a strange connection. This is corresponding to the radius. Like for the circle, the radius of curvature is fixed. It has a constant curvature. So the radius of curvature is also fixed. Like the curvature K is fixed, which is 1 by r for this circle. I will not show this one. And the curvature. This is the curvature, and the radius of curvature is equal to r, both of which are constants. But for a general curve in 2D, this is not constant. This just changes. And for every point, there is a characterizing radius of curvature which corresponds to a circle. And that circle must have the radius rho, or the radius of curvature, and this circle fits the curve at some random point, like let's say P, at P. So there will be different circles, of course, like for here, it will be actually greater, right? Like the curvature is much smaller, so the radius of curvature must be really big. So something like this, or even more, and the radius of curvature will be this. So rho, and you see at every point there exists a circle that fits the best for that curve at that point, and this rho, or radius of curvature, is the property of that point in that curve, right? And as you can see from here, for every general 2D motion, the velocity will be in the tangential direction, and the acceleration will have two components like this. Let's say the acceleration is here, and the components will be in this direction and in this direction. So A, which is parallel to the tangent, and A perpendicular, which is directed in the normal direction, principal normal direction. So normal vector, and this will be directed in the tangent vector. Okay, so that's about it. And of course, this thing corresponds to A perpendicular corresponds to v squared divided by rho, and it means that you can decompose any 2D motion into this portion, into this part and this one, like dv dt, which is the cause of the change in speed. So the acceleration that's in the tangential direction changes the speed, and the acceleration that's in the normal direction changes the direction. Okay, the direction, as we have already told. That's about it. The video has become too long actually. But regardless, I think it was not a bad one, hopefully. So, bye for today. On another note, this two-dimensional thing can actually be a portion. Like, if you are considering a 3D curve, which I cannot really draw right here, if we take a really small set, like really small one, you can see it's kind of in a plane. It's part of plane. What, how do you define that plane? Like I've already told you, you need three points, and 3 points will be like this, and this. So let's say this is the point you are talking about. Let's say speed. This is speed. And there are two vectors. One is velocity. Another one is change in velocity or acceleration, which is just scale. Doesn't really matter. If you use this vector instead of this one, you will get the same plane, right? Just scale vectors. Doesn't really matter. If you use del v or whatever, dv or anything, or acceleration. I think acceleration is a better term here. So v and acceleration creates a plane. At some instant, some really small interval, the kinematics will be restricted to this plane. Okay, restricted to this plane, and this acceleration is also changing because this curve is in 3D. So this acceleration will also be changing, and the change of which might not be in the plane. Let's say it can be here like this, or this acceleration might not have the full component in this plane. There can be like this component, dA, dt, and the component can be in the perpendicular direction, and we're considering perpendicular direction. Okay, so this perpendicular direction will take at the next instant, this will take the acceleration and velocity vector to be something different. The plane will be something different. So that's why I was showing you that 3 points can define a plane, and at every moment, if there is change of acceleration that's directing even partially out of the plane, then the plane will change. Okay, the plane will change. Okay, that's about it. And I think it was helpful enough for some people. Like I don't think who it will be helpful for, but I hope it is helpful for someone. Okay, that's about it. Bye.
Bye everyone. Thank you for watching. See you later.